Welcome to the deep dive. Today, we're jumping into something pretty cool. How zero-knowledge proofs, this really interesting crypto technique, are starting to mix with machine learning.
Yeah, specifically how they might impact things like large language models.
Exactly.
Yeah.
So if you're coming from a blockchain background, maybe you know Ethereum, you've probably bumped into ZKPs already. Think of it like you need to prove something's true, but you don't want to show the actual secret information.
Right. The classic example is proving you're old enough to get into a bar without showing your driver's license. Just some proof derived from it.
Yeah, that's a good one. Like a special token that just says over 21. That idea, proving something without spilling the details, that's what we're going to unpack for AI today.
Totally. And for someone like you thinking from that blockchain sort of trustless perspective, ZKPs bring that same vibe to machine learning.
Okay.
Usually, with ML services, especially machine learning as a service, you kind of just have to trust the provider, right?
Right. Did they actually run my data correctly? Did they use the model they said they would? Is my data safe?
Exactly, all those questions. Zero-knowledge machine learning, or ZKML, gives us a cryptographic way to get answers. Real proof.
Without them having to show me their secret model sauce or my input data?
Precisely. It's all about verifiable computation. It's kind of like extending the idea of verifying smart contracts on-chain, but for these much more complex AI jobs.
Okay, that makes sense. So thinking about how ML works,
Yeah.
Data, training, testing, actually using the model for inference, where do ZKPs slot in? What's the problem they're solving?
Good question. ZKML can actually touch on, well, pretty much all those stages to boost trust and privacy.
Yeah.
So imagine you're a developer, right? You want to use some fancy AI model, say, for sentiment analysis on user reviews.
Yeah.
You send the reviews to a third-party service. Now, with ZKML, that service could give you back the sentiment score plus a zero-knowledge proof.
A proof of what exactly?
A proof that that specific score came from their specific model running on your specific input data.
Ah, okay. So I know they didn't just make up a number or use some cheap different model.
Exactly. And they prove it without showing you their valuable model or revealing your potentially sensitive review data to anyone else. That's verifiable inference.
Gotcha. That's powerful. What about other stages? You mentioned training.
Yeah, so verifiable training is another angle. Maybe you and some other folks want to pool data to train a better spam filter, but nobody wants to share their raw data logs.
Right. That data could be sensitive.
GKPs could potentially let you prove your data was used in the training and help the model without actually showing the data itself.
Interesting. And testing.
Same idea, verifiable testing. An AI company could prove their model hits, say, 95% accuracy on a standard test set without revealing the model wheats their secret sauce. They just prove the performance metric.
Okay, so it protects their IP while still proving capability.
Precisely. It's about building trust cryptographically at different points in the ML workflow.
All right, so let's get a bit more technical. How does this magic actually work? We said ZKPs prove things without revealing details. How do you connect, like running a neural network, to a ZKP? You mentioned arithmetic circuits before.
Yeah, arithmetic circuits are sort of the bridge. Think about any computation, even running a huge AI model. Underneath, it's all just a massive sequence of basic math operations, right? Additions, multiplications.
Okay, fundamentally.
An arithmetic circuit is just a way to lay out that whole sequence formally. And ZKP systems, especially the ones called ZK snarks, are really good at working with these circuits.
So you translate the ML model, the inference process, into this giant math circuit.
Essentially, yes. The model's parameters, the input data, the steps of the computation, it all gets represented in this circuit structure.
Yeah, that sounds complex.
It definitely is. But once you have the circuit, the prover, the ML service, for instance, runs the computation and generates a proof that they executed that specific circuit correctly, arriving at the output they claim.
And the proof doesn't leak the model weights or the input data because those are just like internal values within the circuit computation.
Exactly. Those are the witnesses in ZKP terms, the secret information the proof relies on but doesn't reveal.
Okay. I'm getting a picture. But wait, ML uses tons of stuff that isn't simple addition and multiplication.
Yeah.
Like floating point numbers and those weird activation functions. ReLU is a common one, right? Max of 0 when they input. How do circuits handle that? That seems like a mismatch.
You've hit on a really key challenge and frankly where a lot of the ZKML innovation is happening.
Right.
Standard ZKPs work best with whole number arithmetic, usually in finite fields. Floating points and nonlinear functions like ReLU, They complicate things.
So how do they deal with it?
There are a few tricks. For nonlinearities like real U, one way is to approximate the function using polynomials that can be represented easily in the circuit.
Approximation, so it's not exact.
It might introduce tiny precision differences. Yeah, that's a trade-off. Another technique, especially for things like activation functions or maybe even more complex operations, is using lookup tables.
Lookup tables, like pre-calculating answers.
Kind of. You pre-compute the outputs of the function for a whole range of possible inputs. Then, the ZKP proves that the system correctly looked up the right output for the input it encountered during the calculation.
I see. So instead of calculating real U on the fly in the circuit, you prove you looked up the correct pre-calculated real U result.
Exactly. It shifts the complexity. But building these tables and proving lookups efficiently adds its own overhead. So yeah, handling nonlinearities and floating points is definitely not trivial.
Okay, that gives me a much better feel for the mechanics. Translate to a circuit, handle the tricky bits with approximations or lookups, generate a proof. Now, let's zoom in on LLMs. These things are monsters. Billions of parameters, complex transformer architecture. How on earth does ZKML even begin to tackle that scale? I think you mentioned ZKLLM.
Yeah, CKLLM is a really specific and quite advanced effort aimed directly at making inference for big transformer models verifiable. It's all about tackling that scale and complexity head on.
Now, what are the key ideas?
It relies on a couple of core components. One is called lookup. You can think of that as a super optimized protocol specifically for handling those non-arithmetic bits we just talked about, activation functions, that kind of stuff, but at scale.
Like the lookup tables, but fancier.
Yeah, much fancier. It uses pre-computed tables, but combines them with clever cryptography, like using random linear combinations, to compress the information and make the proofs about lookups much more efficient, especially for the kind of tensor operations you see in LLMs. It's designed to run fast, even using GPUs.
Okay, so lookup handled the non-arithmetic complexity efficiently. What else?
The other big piece is zcaten. This focuses purely on the attention mechanism.
The core of the transformer.
Right. Attention is computationally heavy. zkaten uses specific mathematical properties of how attention works, things like the shift invariance of the softmax function, and combines that with techniques like piecewise linear approximations to create zk proofs for that specific part much more efficiently than a general-purpose approach could.
So specialized protocols tailored to the LLM architecture.
Exactly. Tailored optimizations are key for handling this scale. The whole goal of ZKLLM is to let someone prove, yes, this output came from running this specific huge LLM on this input, without giving away the model weights and doing it relatively efficiently. They've shown it can work for models with billions of parameters.
That's really impressive. I also saw mentions of another approach, something using Volet. And range proofs, how does that fit in?
Right. The work by Liu and colleagues, that's another angle on improving efficiency, especially for the nonlinear parts. Volet stands for Vector Oblivious Linear Evaluation. It's a different kind of cryptographic tool. Think of Volet as helping handle the linear algebra, the matrix multiplications, within the neural network more efficiently in a zero-knowledge way. Then they combine that with range proofs.
Range proofs, like proving a number is within a certain range without saying the number?
Exactly. Useful for checking activation function outputs or maintaining numerical stability. So they combine Volet for the linear stuff, range proofs, and also lookup proofs to try and simplify the overall ZKP circuit needed.
Making it faster to generate and verify the proofs.
That's the idea. It's presented as being a bit more modular, potentially applicable to different types of networks, not just transformers. And yet, they reported some pretty significant speedups compared to some earlier methods. It just shows how fast this field is moving.
Definitely. All this progress on verifiable inference, it makes this idea I read about the zero-knowledge court for LLM agents seem more plausible. What's the concept there? As a developer, that sounds intriguing.
Yeah, it's a really cool concept pointing towards accountability for AI agents, especially if they operate in decentralized settings like on a blockchain.
Accountable how?
Well, imagine you have an AI trading bot powered by an LLM running on-chain. How do you ensure it's playing fair? Maybe it needs to prove it actually paid the right gas fees, or the API costs it claims it incurred, or that its use of context windows lines up with its actions.
So proving its operational costs or actions were legitimate.
Right. A zero-knowledge court could be a system where this agent submits ZK proofs of these things, proofs it paid the fees, proofs its computation followed certain rules without revealing its secret trading strategy or its full internal state.
And if the proof fails?
Then the court knows something's wrong. Maybe the agent faces penalties. It creates this mechanism for verifiable accountability, which could build a lot more trust in autonomous AI agents interacting in economic systems.
That could enable some really complex on-chain AI applications. Okay, so we've talked a lot about LLMs. What about other concrete uses for ZKML that are popping up? And what's out there for developers who actually want to try this stuff?
Oh, the potential applications are spreading out. We're seeing actual projects working on things like verifiable AI trading bots, like you mentioned, blockchains that can verifiably improve their own capabilities using AI, maybe for an image recognition or something.
Wow.
AI-driven reputation systems where the scoring is transparently verifiable. For blockchains focused on privacy, ZKML could allow smart contracts to use ML for compliance checks on encrypted data.
That's a big one. What about outside finance and blockchain?
Definitely. Think healthcare, using CKLLMs maybe to analyze encrypted patient records for diagnostic suggestions without ever decrypting the sensitive data.
Huge privacy win there.
Or personalized financial advice based on encrypted financial data. Secure chatbots where your queries remain private even from the service provider. Even things like content moderation on end-to-end encrypted platforms.
Okay, lots of potential. Is it accessible yet? Are there tools?
It's getting there. The ecosystem is building out. There are libraries like ESCL, which is pretty interesting. It lets ML engineers take models they've already trained and exported in a standard format like ONNX.
Oh, NNX, yeah, that's common.
And generate zero-knowledge proofs for them. It tries to abstract away some of the deep crypto complexity.
That lowers the barrier to entry quite a bit.
It does. And then you have companies really focusing on this space. Modulus Labs, Giza, Ezekiel are names you hear building infrastructure and tools specifically for ZKML.
So there's commercial activity building up.
Absolutely. People are projecting the overall market for ZK proofs to grow significantly, billions of dollars by 2030. That implies a lot more ZKML usage. And you even see hardware companies like Ingonyama building special chips just to speed up ZKP generation.
Hardware acceleration makes sense, given the computational cost.
It'll be crucial, yeah, especially for bigger models and real-time applications.
It definitely sounds exciting, but also challenging. It feels like we're still early. What are the big hurdles ZPML still needs to overcome?
Oh, for sure. Early days, definitely. A major one is still the sheer computational overhead. Generating these proofs, especially for large models or big data sets, takes time and resources. Verification is faster, but the proving part can be a bottleneck.
Right.
And while there are techniques to help, like some specialized snarks called CP snarks that try to reduce the cost related to verifying the model and data commitments, it's still significant, especially for that verifiable testing case we talked about.
Okay, so performance is still a work in progress. What else?
Generality is another thing. Right now, many ZKML solutions are kind of bespoke. They need to be carefully designed and optimized for a specific machine learning model or even a specific type of nonlinear function.
Because of that difficulty translating ML math into the ZKP's finite field math.
Exactly. Building truly general-purpose ZKML frameworks that can easily handle any ML model is still a big research challenge. We need more progress on efficiency, yes, but also scalability for even bigger models.
So optimizing the circuit designs, maybe new ZK protocols, specifically for deep learning.
Precisely. And things like recursive proofs, where you can verify a proof inside another proof, might also help with scaling things up. Lots of interesting research directions.
Oh, this has been seriously illuminating. It really feels like plugging ZK proofs into machine learning could solve some fundamental trust and privacy problems.
I think so too. Being able to prove an AI did what it was supposed to do without forcing everyone to reveal their secrets, whether it's private data or valuable models, that's potentially transformative.
Yeah. It feels like a shift from just cool research papers to actual tools and companies starting to build real applications.
Definitely. The ecosystem is growing, the tools are getting better. It's an exciting space to watch.
So for you listening, especially if you're a developer thinking about this, here's maybe a final thought. If we can cryptographically verify AI computations, what does that unlock? What kinds of decentralized apps or collaborative AI systems become possible when you remove some of those trust barriers?
Yeah, how does verifiable AI change the game for the kinds of systems you could build?
It's definitely something to chew on. Maybe check out some of those companies and tools we mentioned, like ESCL, if you want to dig deeper. Thanks for joining us on The Deep Dive.